Right. Hopefully I got the microphone right. It's the first time I've used one of these. Right. So hopefully everyone's looking for Wireshark and TLS and stuff like that this afternoon, and not expecting to be in the other room. So who am I? Why am I talking about this? So I spent kind of the last 20 years working at an ISP, specializing in education, and we were having to do lots of filtering, and so spending lots of time looking at TLS and trying to understand these changes for TLS and what they're going to mean for us. And yeah, currently work as a cybersecurity engineer for ERM. So why has this change happened that people are looking at improving TLS security? So people remember this photo taken from when the Edward Snowden revelations came out. They caused people to start thinking about what metadata was around and how they could encrypt it better. So brief history of SSL and TLS. So SNI was introduced with TLS 1.0 and kind of became a thing in 2006 when IE7 and Vista came out. So people have got used to the idea that this SNI information's there, and it's in clear text, as we'll come on to. You can see the other versions of TLS have come out afterwards, but they've left SNI alone. TLS 1.3 made some changes, but it still left SNI alone. So what is SNI? So server name indication. So it's a plain text header that when you browse to a HTTPS site, it's there in the clear for anyone to look who's looking at that message using a TCP dump or whatever. And it's in the client hello negotiation. And it's been used by lots of corporate firewalls and nation states as well. So it was built for one purpose, which was hosting lots of websites on one IP address, but it's had alternative uses by the security community to find out what's going on the network. And I've kind of put around the abused because the writers of the SNI standard, the people on the TLS committee, don't think that those are legitimate uses of the SNI information. It's obviously a difference of opinion between different people. And yeah, the key is once you've encrypted DNS with DNS over HTTPS, then the SNI information is the last plain text piece of information out there. Although the IP address you're going to is kind of in the clear as well. But again, Cloudflare and other people have solutions to that. So, how's it been used by nation states? So, as an example, South Korea moved their filtering from DNS to SNI filtering, and there's one of the large Indian ISPs also started to do filtering based on SNI. So there's evidence that SNI is being used at a nation state level to do filtering, and this is again encouraging the people making the standards to try and fix this problem. So, who is making these TLS standards? So, assuming most people probably have heard of Internet Engineering Task Force and RFCs, but there's a group of people from different companies. They might be from Google, from Apple, from Cloudflare, working together to come up with these standards and get them ratified and then adopted by multiple companies. So they're often doing it, sort of outside of their day job, but they are also still representing their employers. And you get lots of RFCs. Some of them have been created as RFCs, real numbers, but never actually implemented because they're kind of jokes or whatever. And there's others like the one at the top, which I'm sure nobody at the back will be able to see, but the RPZ one that's used for DNS filtering, which never made it beyond being a proposal because the committee didn't want to agree to things that promoted censorship. So stuff that just because it doesn't make it as an RFC, it doesn't mean it's being used. And also just because it's in an RFC, it doesn't mean it will be used. So you have to view it from that lens. And one of the ones I spent many afternoons trying to think of a network authentication required one that was in one of the RFCs. And no captive portal actually does it. So it's in the RFC, but nobody's ever implemented it. So what happened with TLS 1.3? So in TLS 1.3, lots of people probably will remember when it came out, there was a lot of furore about it stopping people understanding what was going on the network. And what they did was they encrypted the certificate that comes back from the server. So the observer now can't see the certificate that's coming back. But the SNI header that went in the connection message is still in the clear. So it reduced for confidence as to what somebody was going to, but it still left a pretty big clue as to what somebody was going to. And kind of removing that SNI header is then unfinished business for the TLS 1.3 people. And so, yeah, they encrypted the handshake. And one of the things they had to do is put this middle box compatibility mode in. So this was because when they tried to release TLS 1.3, they had all sorts of problems with people with various firewalls not understanding TLS 1.3 and crashing. And so they put in a way of making it look like 1.2 to these, what they describe as middle boxes, so that they don't crash and still process the message, and it aided TLS 1.3 adoption. So again, while they've been working on encrypting SNI, they've also been working on the same principle. They don't want to break existing networks, and they want to make it easy for people to roll this out. So what are the people's aims with this? And it started off as encrypted SNI, and it's now become encrypted client hello. So you'll see in the RFCs, it mentions both names kind of, but yeah, the new name is encrypted client hello. So remove this last piece of metadata, don't stick out, and make it hard for somebody in the middle to downgrade the connection. So if the client and the server both agree that they're going to do ECH, then nothing in the middle should be able to force them not to do ECH. Your corporate firewall shouldn't be able to prevent it if both sides have agreed that it's a good idea. And the aim is really to be using this with large-scale providers like Cloudflare. So it makes it difficult to just say, I'm going to block that provider, because you're blocking thousands of sites. And so Chinese government might do that, but lots of other governments would balk at the prospect of blocking Cloudflare. So why is this hard? Why hasn't it been implemented already? So the challenge is you've got to send this SNI information before you've negotiated any keys. So you need a mechanism of doing that, and you need to be able to support CDNs that serve thousands of websites. Before SNI came along, one IP address to one website was fine. That wouldn't be fine anymore. And they want to try and make it not stick out. And they want to ensure that they don't break existing network appliances. So how did it work in TLS 1.3 already? So you can see here the plain text headers come through, and then you've got your encrypted certificate going back. So and here's an example of a header then going through the server name in the SNI. So it's very much in the clear. You're sat there with Wireshark, you can see exactly what's happening. So the first attempt to do this was ESNI. This got as far as being implemented by Cloudflare and Firefox, and it worked by having a text record with the public key for the exchange, and it just encrypted the SNI flag. But it ran into a number of problems for large-scale CDNs and DNS caching issues, and it stuck out too much, and the Chinese government pretty quickly worked out that they could just block anything with that header, and everyone went back to the drawing board. So they came along with the idea of encrypted client hello. So this hides the whole of this hello message with an inner hello with the real information. So you've got an outer hello wrapping it, and then the inner hello tucked in inside. And we'll talk about how that works in a minute. The key is it's not just hiding the SNI, it's also hiding things like ALPN, which tells you what protocol you're using, HTTP2, HTTP 1.1, and other things. And the outer hello helps with decryption failure. So again, trying to make it more resilient to network appliances and things. So the way that the authors of this standard are intending it to be deployed is not on a kind of one-to-one basis, sort of this top model where you've got one server and you've got one key. The intention is much more that you create this anonymity set where you've got a client-facing server that has thousands of websites on, and is then proxying it down to the back-end server that might be somewhere completely different. So very much Cloudflare's normal hosting model. And the aim is that you should use the same ECH config for all of those 1,000 sites that Cloudflare are hosting or whoever is doing it, so that all you know is it's one of those sites that somebody's going to. You can't work out what the site is. And inside that bucket, there might be the phishing site that's targeting your network, your corporate site, and loads of other sites inside the same bucket. So how are we going to exchange this key before we've started the connection? So there's a new DNS record that's going to be created, or is being used called a HTTPS record or type 65. And that stores a load of extra information in it. So if we look up, and sorry, this text will be too small for people at the back, but if you do something with KDig and you ask it for type 65, you get a binary blob of data back if you look at Cloudflare's record where they've got this set up. And it's not very easy to understand, but there are some of the tools that have now been upgraded to be able to dig into this. So Drill is an example. It's written by NL Labs, the same people who do Unbound. It's a different tool set written by them. But Drill will open it up, and now you can see that it's got a load of text information, but then it's still got an encrypted blob of data that's it's in base 64, but we don't know what's inside it at the moment. And then some IPv4 hints and ALPN information. So this HTTPS record is doing much more than just exchanging the keys. It's giving the client an initial idea about how to connect to the backend server without having to negotiate any further. And you can see Wireshark now understands it. And if you look at these, when you've captured them in Wireshark, Wireshark will also decode them for you. So what's inside that ECH bit we saw? So if you look at, and this is a different site where they didn't have the other BALPN and the IPv4 hints, they just had the ECH bit. But if you look at here and you run this through this ECH CLI, which comes out of a fork of OpenSSL, and I've put the link at the end if people want to download it, but it neatly decoded the information inside it. So you've got some information in here, some sort of magic numbers that we'll come on to later, a fake SNI information that it suggests you use, and then an encryption key. And in this case, there's 2 of them for this site, so it allows them to rotate their keys. Another example from Cloudflare, where they've got the other information in, you can see in the ECH config again, you can see their fake information to send for the SNI, and then a single encryption key for this one. And that key is based on a new standard that's also been ratified as an RFC, and the same people are involved in creating this new HBKE. So you can see there's a Cloudflare blog. A load of these graphics off this presentation got stolen from Cloudflare because they've got the best graphics for this. And yeah, this is not just used for exchanging ECH. It's intended as an all-purpose tool, but this is one of the first applications of it. And there's some other goals that they're intending to do with this new flag, and one of them is to be able to do the ECH bits, but also enable people to go directly to HTTP3 if the backend supports it, without having to guess, without having to probe it and then see. We know the backend supports it. They've put the message out there to say that HTTP3 is available, or HTTP2, and also to allow you to specify that you're using non-default ports. And again, like the HSTS thing, allow you to say, I want to go straight to HTTPS. So this standard is not quite there yet. It's still in draft, but it has been widely implemented. And the challenge, and this came from a slide from one of the IETF committee meetings from 2 months ago, they've had to bounce the thing because the 2 standards are kind of intertwined and they're waiting to get one ratified to get the other. And they've now split part of it out into a separate standard. But we will see the HTTPS DNS record get ratified first without the ECH information, and then they'll come on to do that afterwards. So how many of those DNS records are out there and what have they got in them? So I looked at the Open DNS 1 million list, which is disconcerting train whistles. So you can see that there's sort of 84,000 of that 1 million who've published these HTTPS records already, despite the fact it's not an RFC and it's not yet a thing. So that's pretty good adoption for something that's not yet an RFC. And most of them have got IPv4 or 6 hints, and there's a load of APL information. And just for a laugh, I had a look on what's inside that as well. So you can see that quite a lot of them are specifying that they can do HTTP3, which I was slightly surprised by. The percentage that were suggesting that. And And yeah, it's just kind of slightly useful information. There's also some that are saying they explicitly support the pre-release, the original quick version, 3.27 as well. So this is obviously being sent as DNS. DNS is plain text, so sending keys as DNS, is that a good idea? So traditional DNS, you know, your browser talks to a resolver and everything's over plain text. But when the browsers are doing ECH, they're going to insist that you're also doing DOH, which means that the workstation or the browser in the workstation is talking directly to your cloud provider. So it will, if you're using DO53, it won't even try to do ECH. It's my current understanding for the implementations. Obviously that might change when these get from preview to release. But at the moment, they're insisting that you also do DOH and do DOH in the browser, not DOH further downstream, because the browser needs to know that it's done DOH. And yeah, and for anyone who hasn't seen it, you know, DOH was a more recent RFC. And it basically sends the DNS request as a binary DNS request, but over a get and post over HTTPS. And it's also kind of hard to block, which is one of the other challenges with it. And yeah, current implementation in Firefox and Edge, it only uses ECH if DOH is also used. So kind of preparing for this, kind of had a look at what example code is around for ECH at the moment. So if you want to set up the server side, OpenSSL, there's a fork that's been written by a team and published on GitHub that you can download and build, and works great. And that's how I did those ECH dumps using the OpenSSL fork. There's an Nginx version that also depends on that OpenSSL fork, and you can build it. And then there's also completely separately a Go client server written by one of the Cloudflare people, but relies on the Cloudflare fork of Go, I think, because of that encryption, which, yeah, you can get set up and works. So browser support for it. So Firefox, it's already in the regular build, but you need to turn it on and you need to have enabled DOH. Edge, a bit more of a faff to turn on. So you need to turn on using that new DNS record flag, which has got a slightly confusing name, and then enable features when you restart Edge, and also enable DOH. I found Firefox to be really reliable. You just turn it on, you turn it off, and it just works for ECH. Edge I found to be flaky, to say the least. Chrome, you could turn it on nice and easily, but it only worked with one of the two test sites. And so there was definitely something slightly flaky about what Chrome had done. And so Cloudflare's test site shows you that you're using SNI. Doesn't really go into how it's working under the hood, but it gives you a nice overview. And this site I found to be much easier. So this site, if SNI is off, it tells you exactly what it was sent. It didn't see anything exciting. And then when you turn ECH, in fact, and you can see also in the packet trace, you can see the original SNI that matches the what you see in the top, as you expect. And then when you turn on SNI in the browser and ECH in the browser and reload, you see the success. So now you see this outer SNI, which is what the observer on the network sees as the cover. Where's it gone? Yeah, cover. Now, they've chosen to use two names that are very similar, but obviously the intention is in the wild, that outer name would be something that bears zero resemblance to your site and is just a generic name. And so if you've captured it, you haven't captured anything at all. And the inner one is the interesting one. But for the purposes of their examples, both Cloudflare and this other site have chosen to put a name that relates to their real site in there. And yeah. And again, in slightly more detail, so without ECH, the other thing they've also, as part of this, suggested that the browsers are going to send this extra grease flag. So when you're not doing ECH on a ECH capable browser, it will still send extra data in and pad it out using this grease field at the bottom, which Wireshark understands as grease and shows it as a reserved extension. And then with ECH, you now see, and this is because Wireshark doesn't understand it yet, you see this unknown type, and that 65037 maps down to that FEOD that we saw in that DNS record. And you've got an encrypted blob of data there, encrypted using the public key that was in the DNS. Obviously, without the private key, we can't prove that those match, but, and yeah, those numbers. So, it's in the standard that it's going to be that FE0D at the moment. I'm kind of expecting them to change that before it becomes a ratified RFC, because it's in the middle of a reserved for experimental use field, but maybe they'll keep it as it is. I don't know. So why does this matter? And how do people filter HTTPS today? So, like, you've got stuff that works down at a workstation, totally not impacted by ECH. So, like, Windows Defender, web content filtering, works as an API, works before the DNS request is made. Life is straightforward. You've got proxy-based stuff. You'll still see the proxy connect message, so far as I'm aware. And that should not be impacted by ECH as well if you put it as an explicit proxy or a pack file, because the proxy connect message is telling where you're going to go. You don't have to rely on the SNI information. The one that's the challenge is where you haven't configured a proxy explicitly and you're trying to do it in a firewall or Squid or Zscaler, and you've not configured anything and you're doing it transparently. So, and often the same things will do proxy and transparent, so the same brands in both. But most of these tools have both ways of working. And transparent's great if, for instance, you're a school network and you want sixth formers to bring laptops in and not have to configure proxy settings, but still get some filtering. So there's lots of use of that transparent filtering. And that's where ECH will really scupper it, because it just will not be able to see inside. It's going to use the SNI and it'll only have the outer SNI, which will be useless. And yeah. So I think this is the one that's going to be broken. There might be ways around it. So if you can stop the DNS message going down, and you can prevent people talking DOH, then you can probably prevent it and keep the transparent filtering going. But it will rely on now being able to block the DOH message, block the DNS message to make that work. And said earlier, that's not always easy because there are so many different DOH providers. So how can this be used for kind of nefarious purposes? Well, it's kind of too early to see exactly how ECH will be used. But what we do know is the DOH stuff has definitely been used for nefarious purposes. People have found out ways of hosting C2s on, and using DOH as part of their C2, or building a complete exfiltration kit using DOH. So my assumption is that ECH will also, be used for good and for bad, and people will work out ways of hosting their C2 using ECH to hide in plain sight and pretend to be Google and slide out if you've got a network that makes that possible. So, is this good or bad? Well, it's happening whether we like it or not. And different people's threat models. So if you are caring about privacy on your local network and you're not trying to filter, then this is great. People upstream cannot tell what you're doing. That is probably a good thing. But if you're a corporate network and you're relying on these tools to work out what your users are doing, then yeah, that might not be so good. And so, looking at it from a sort of CIA confidentiality point of view. So, if the question is, who are you really being private from, and who does ECH help you with? And yes, it probably does make it more difficult for those top four to see what's going on. But, you're still going to that large American advertising broker. They can still see what you're doing. It makes no odds at the end. And integrity, well, it matters much less for that because that was already pretty good with regular TLS. Availability is the more interesting one. We know that DNSSEC has had all sorts of issues where people have screwed it up and broken their websites, Slack not so long ago. I think ECH has a good opportunity for more foot guns, ways for people to shoot themselves in the foot, break their key rotation. And also, it's going to encourage more consolidation onto those large players like Cloudflare, who have the ability to operate this, have the ability to do that key rotation, and people choosing to use those players to host the websites if they want to take advantage of this. And I think there'll be a people that are impacted by this in terms of losing their visibility of the people in the middle of this network management spectrum. So you've got kind of unmanaged at one end, and then you've got your tightly managed enterprise at the other end. And it's those people in the middle who have some lightweight filtering at the moment, works in the network, using a firewall, using a Squid proxy server or whatever, who will really struggle with this because they'll suddenly lose that visibility and they'll be forced to either go, yeah, okay, sixth formers, you can do what you want, or actually, no, sixth formers, you're not allowed to bring laptops into the common room. Have to go one of the two ways because you won't be able to live in the middle. And yeah, so considerations for enterprise networks. What things are you relying on that SNI information for today? If it starts lying to you, will you know where are you getting that data? And yeah, are you using it for things like BYOD to do filtering? Is it possible to get to an explicit proxy rather than transparent? And yeah, maybe moving more from the network to endpoint security, because again, things like the Windows Defender, where it works on the device, you're still guaranteed that visibility. So EDR solutions are great, but they'll still have the visibility. It's the network solutions that are less good. And then, yeah, at the end, lots of links that I use to grab the information for this, because obviously most of it's not my own work. A lot of it, pictures are stolen loosely from Cloudflare's site. This link at the bottom is particularly interesting, though. There's been a group of industry people sat on calls on a Monday afternoon, and those calls are recorded and put on YouTube. And so if you're interested in this field and interested in DNS or interested in the changes to TLS, it's well worth looking out for those calls and listening to them, not just on this subject, but on a load of others. It's a really interesting venue that you've got people from Google, people from Apple, people from Microsoft talking. And in the open, recorded into YouTube, so anyone can go and listen. And yeah, and then there's some more of the resources used. Yeah, questions? So yeah. That's a good question. I mean, they can go down the China route with ESNI and just say, yeah, we're going to block that, and probably end up having to block the whole of Cloudflare. I think if you can stop the DNS message going down, you can prevent the negotiation. So if you can stop all of the DOH entry and you, on the regular DNS entry, you filter out the type 65 messages, you could probably stop it negotiating with some degree of confidence. But getting that block on DOH is really hard because people will pop up ones on different IP addresses and you'll never find them. Any other questions?
Do you think there's any, do you think people would take the approach of large-scale traffic analysis to kind of figure out where people are going?
And I think that is definitely the thing that we're trying to do with the anonymity sets, to make those sets as wide as possible, to make that as hard as possible. And so all you'd know is somebody's going to a Cloudflare hosted site or whichever CDNs choose to implement this standard. But yeah, where somebody is hosting their own C2 and has chosen to build their own ECH config to hide their own C2 on a VPS somewhere, yeah, that will stick out like a sore thumb if people are doing that analysis.
Is there anything else that's missing from my TLS? So this is like fixing the update text SNI. Is there anything else that's...
I think the other sets of changes they're looking at are like the HTTP3, the quick getting to UDP, and there's also again changes being talked about to do DOH over quick as well, DOQ, and yeah, things like the Apple Private Relays solution and standardizing that. There's the Oblivious kind of solutions where they're trying to enable that kind of proxy solution and make it easy for people.
One of the things that was quick, which was really fronted a lot by Google for their own purposes. I certainly know from a business perspective, a lot of companies block quick now at the edge because the companies themselves are starting to lose control of what Google is telling the browser or the system at the end through the quick messages, what it can access and can do.
Yeah, absolutely.
So this one's going to be a bit of almost another battleground.
Yeah. I think, and again, you see it with. I've also seen it with H2 with regular H2 as well. So if Chrome talks to Google and it negotiates itself as a H2 connection, you see the SNI as being google.com. You then in that browser go to youtube.com. You don't see another connect message. It just reuses your existing connection and downloads YouTube over it. And obviously that only works for things that are hosted by the same company, but Google and YouTube hosted by the same company. But as an enterprise, you might have a different policy around YouTube in the office to Google in the office, particularly schools do. And so, H2 already causes that problem on transparent networks, and H3 will as well. No other? Thank you.